Question 7 from the 2022 National 5 Physics paper from the SQA Section 1. Which of the following lists the distances from the longest to the shortest? Well, what have we got? We've got the diameter of a galaxy, we've got the radius of the orbit of the Moon round the Earth, and we've got the radius of the Earth itself. Well, the first things first, the longest must surely be the diameter of the galaxy, and the second must be the radius of the orbit of the Moon, when you think about that, and then finally you've got the radius of the Earth. You're going from a galaxy to an orbit and to the actual planet itself. So the answer to that question is going to be C. Just to recap, we have got a galaxy. You don't have to remember these figures, but it's worth knowing the distances. The diameter of a galaxy is enormous. It's 22,000 light years. It's better to measure it in light years rather than meters. It's so big. So 22,000 light years. If you were to travel from one end of that galaxy to the other at the speed of light, it would take you 22,000 years to get there. Now, if we look at the Earth and the Moon, you can see that the distance between the Earth and the Moon is going to be its orbital radius, and that's 350 million metres. So that's why it comes in second place. And of course, the radius of the Earth is 6,371 kilometres. So our answer to that question has got to be answer C, because we've got the diameter of the galaxy coming the longest, the radius of the orbit to the Moon, and the radius of the Earth. So the answer is going to be C. Question 8. 3 satellites X, Y and Z are orbiting the Earth as shown. The diagram's not to scale. And we're told that satellite Z is a geostationary satellite. And we're asked to find which row in the table would show the possible periods for the orbits of X, Y and Z. Well, the big clue is the geostationary satellite. The period of a satellite is the time it takes to make one complete orbit. And a geostationary satellite has got a special period. For a geostationary satellite, its period is 24 hours. So it appears to be above the same spot on the Earth as we see it from the Earth. That's why all your satellite dishes are pointing in the one direction, because they're pointing to the direction of a geostationary satellite. So a geostationary satellite has got a period of 24 hours. Now, the other bit of a clue we have to know about satellites is this important fact here, is that the smaller the orbital radius, the faster the satellite must travel. And if the satellite is travelling faster, it will make one complete orbit in a shorter time. So what we should see then is that satellite Z should have a period of 24 hours. So that gives us the following options. It gives us this option here, and this option here, and this option here. But any satellite nearer the Earth will have a smaller period because it's moving around the Earth faster. So obviously this one here is ruled out because satellite Y is the same period as satellite Z, and they're in different orbits. So we can rule out this one here. That's out of the question. The one here is ruled out as well because the satellite Y is in a lower orbit, and therefore it's going to move faster around the Earth, therefore it's going to have a quicker or a smaller period. So we can rule that one out there. So the only viable one there has got to be this one here, A. The period of the satellite Z, being a geostationary satellite, is 24 hours. And if we go closer to the Earth, the period will decrease, 18 hours for satellite Y, and if we go further closer to the Earth, X, the period is going to decrease more, and we're going to have satellite X having 12 hours. So our answer to this question is A. Question 9. A spacecraft has 4 rocket engines P, Q, R and S and is travelling to the right as shown. When switched on, each rocket engine produces the same amount of force. And we're asked to find out which rocket engines are switched on to reduce the speed of the spacecraft. Well, if you're travelling from the left to the right in the direction of the arrow, you want those rockets to provide a force which is going to be from the right to the left. And that's going to provide the forces which will produce the acceleration or the deceleration to stop the rocket moving from the left to the right. So we have to fire these rockets here. Because if we fire these rockets here, they're going to provide a force, shown with the blue arrow, in that direction. Remember your Newton's third law. The rocket pushes out the hot gases, and the hot gases pushes back on the rocket. So these blue arrows here as a result of the force due to the rocket pushing out the gases as shown. So which engine should we actually use? Well, to get the rocket to slow down, we should be using these two engines here, R and S, for those reasons which we just talked about.